in today. Always appreciate anybody who takes the time out to, think a little bit about EMC and think a little bit about how it can apply to, the work that you're doing day to day. I wanted to introduce myself as both a principal scientist for EMA, electromagnetic applications here in Denver, but I'm also transitioning to my own company. So my own company is EMC United. We're in that transition period where I'm still supporting both. For instance, I've got a website, www.emcunited.com, but not a LinkedIn page yet. So if anybody wants to reach out for either company, just let me know. So speaking today of unintentional antennas, one of the things that I wanted to do when I first put together this talk is I knew that my audience would be very broad, and there would be people who were just starting out, who've, are encountering these topics for the very first time. And for folks like that, I want to make sure that you get some fundamentals, some basics on how this weird world of electromagnetics can manifest itself in ways that, that are a little bit counterintuitive, and some of the common pitfalls that you should watch out for. But for folks in the audience who, have decades of experience or, very deep depth of experience in these topics, I also hope that you'll get something out of this as well. And in particular, some examples and some analogies and some language that will help you communicate some of these very strange topics to non-specialists. So that might be, management, it might be customers, but it might also be, other engineers who just have not had the same exposure to electromagnetic compatibility. So with that, I always like to start out, what is EMC? So EMC, electromagnetic compatibility. And my elevator pitch for EMC, when people are like, what do you do? Is, when you have to pack a lot of electronics into a platform, and that can be a phone, it can be a satellite, it can be an aircraft, a car, you need to make sure that they all play nice together. There's some synonyms, so related acronyms are EMI, so for electromagnetic interference, EME, E cubed. A new one is EMR, so that's electromagnetic resilience, and this is a topic of active research, particularly in Europe, where the idea is that because we can't test for everything, we need to design for resilience. So if you ever get a chance to look up some of that research, I highly recommend it. But most people encounter EMC in terms of, oh dear, I've got an EMC problem. Now, to have an EMC problem, you need three things. And I kind of refer to this as the fire triangle of EMC. So the way a lot of us learned that to have a fire, we probably learned this in elementary school or such, to have a fire, you need to have a heat source, fuel, and oxygen. And if you take away one of those things, then you've put out the fire. For EMC, you need three things. You need a noisy source, a sensitive victim, and a coupling path between them. And that coupling path could be through, if you've got multiple things plugged into the same power bus, then you get conducted interference. But then if if that's not the case, what we're often dealing with is radiated emissions that are coming from a noisy source and interfering with a sensitive victim. A real world example of this, and it might seem a little trivial, but it's such a great illustration. So a colleague of mine posted on LinkedIn that they'd bought a new refrigerator. So this is back in 2021. They'd had a refrigerator in their kitchen for years. They'd always had an FM radio right next to it so that, as they were cooking dinner or what have you, they could, listen to the news or listen to music. But then finally that refrigerator got to the end of its lifespan and they bought a new one. So they left the, FM radio in the same place, not thinking anything of it. But as soon as they would open the new fridge door, the FM radio would fritz out. And that's just a classic radiated emissions problem. And one of the interesting things is that, the refrigerator as a whole was almost certainly tested to FCC compliance limits. And those limits are set at, either 3 meters or 10 meters. So what we call the far field. I imagine that when the door opened, it was much closer. It was probably, a meter or less next to that FM radio. So, this is probably a compliant how do you say, refrigerator. It's just a matter of it wasn't tested or designed for that kind of compatibility. And so it's really that radiated path that is going to be the focus of this entire talk. And basically what it comes down to, now it used to be that I could just say who would put an antenna in a refrigerator, but now we have smart refrigerators, that can probably communicate on Wi-Fi and Bluetooth. So now I have to say who would put a non-Wi-Fi or non-Bluetooth antenna in refrigerator, and specifically the kind of antenna that could affect an FM radio, which of course is hanging out between 88 and 108 megahertz. So one of the issues is that we tend to all think we know what antennas look like, right? So you've got the really big antennas that can talk to space, like the Goldstone antenna here from NASA. You've got the old rabbit ears that you used to have to mess with, like long ago. You'd have to mess with these kind to get your good TV reception over the air. And of course now, probably the vast majority of people in this audience are wearing an antenna of some kind on their person right now, right? So, in your phone, in your smartwatch, there's no end of Internet of Things where, you've got antennas integrated into a device. The problem is that this right here, this power brick, this is also an antenna. And how do we know that this is also an antenna? Because of that thing. So that is a common mode choke or a ferrite. The only reason it would be there is if this particular device went in for FCC or some other regulatory testing, failed radiated or conducted emissions limits, and then had to add this to suppress the noise that's coming out of it. And the consequence of this, I mean, it might seem pretty easy to fix, right? You have a noise problem, you add this ferrite, and now you don't have a noise problem anymore. The problem is that you've now added cost, however many cents every ferrite is going to cost on every power supply that this manufacturer is making. And you've also shortened the lifespan of the unit, because having that mass there, because that ferrite is made of iron or some other ferrous metal, so it's pretty heavy. It's putting extra wear and tear on that connector, and so it's going to shorten the lifespan of the entire device. So there are real downsides to finding these problems so late that ferrite is your only option. And so one of the things that we're really going to talk about in this particular presentation is, how do things like this happen? Where can you spot them, and how can you try and fix these problems in the design phase so that you don't end up adding cost and schedule and weight and redesigns at the very end of your product lifecycle. So when I started teaching this topic, I started to explain antennas, and then I realized that there was a fundamental level where I did not understand how antennas worked. And it really kind of goes against intuition, right? Because we've always learned that no current flows in an open circuit, right? So when the switch is off, there's a break in the circuit, there's no current flowing, and then you close the switch, you create the conducted path, and you have power floating to your light bulb or what have you. So how does current flow in a system like this? This is a classic center-fed dipole. There's no conductive path between the two arms of the dipole. There's a voltage source between them, but there isn't a conducted path between them. It really looks like an open circuit. So after I spent a lot of time thinking and reading and thinking and reading, what I really came up with is, an antenna is just a really bad capacitor, and a capacitor is just a really bad antenna, but they are fundamentally different manifestations of the same effect. So what we end up having is the higher frequency current that quote unquote flows through a capacitor is actually called the displacement current. And if you ever get a chance to look at the original formulation of Maxwell's equations, so the formulation, the way Maxwell actually wrote them down and published them. It's 20 equations instead of 4. We have 4 now because thanks to a really wonderful genius named Oliver Heaviside, who came up with a more elegant formulation that we have now. But displacement current actually used to be an explicit term in the original version of Maxwell's equations. Now it's implied by the later version, the 4 equations that we all know and love, but it's easier to forget that it's there. So basically, when you have a potential difference between 2 conductors, when it's 2 plates and there's a DC, DC current charging up a conductor, then we're used to thinking of the capacitor storing the electric energy. So it's storing energy in the electric field between the 2 conductors. And then, when you discharge the capacitor, then, all that energy comes flowing out. But of course, we all know, in an AC circuit, and, we see this by placing decoupling caps everywhere, right? AC current can flow through capacitors. And so basically it's the same effect. It's called the displacement current. But it's just a matter of, instead of storing all that energy and stopping, it stores it going one way and lets it go one way and then the other way, and it just flips back and forth however many million times a second. Now with an antenna, it's doing exactly the same thing. It's 2 conductors with an RF potential difference between them, so a high frequency potential difference between them. But in this case, instead of storing the energy, it's literally broadcasting the electromagnetic fields out into the universe. So fundamentally, when you think of it that way, all it takes to make a dipole antenna is 2 pieces of metal, so any 2 conductors with an RF potential difference between them. And I'm going to repeat that like a dozen times in this talk, so just a warning. But there's an analogy from Henry Ott, and Henry Ott was, he's since passed away, but he's the author of one of the definitive textbooks for EMC called, appropriately enough, EMC engineering. But he had a really good analogy. So if you want to generate sound, you can do that by using 2 hands to clap together. Your hands come together and make the sound, and then they come apart so they can clap together and make the sound again. It's very similar to how the potential difference between the 2 ends of the dipole are letting you generate these electromagnetic waves. But another classic antenna is monopole. So that's only got 1 arm. How's that generating electromagnetic waves? Well, there are actually still 2 conductors between them with an RF potential difference between them. It's the single antenna element, so the arm of the monopole, and then the reference plane, which you'll often see referred to as the ground plane. And if you've seen other EMC talks, there's a lot of baggage that goes along with calling something ground. But again, you still got 2 conductors with the RF potential difference between them. Now, in our hand clapping analogy, if you still want to make noise by clapping, but you have to keep 1 hand in your pocket, you can clap your free hand against a table or a cabinet or a, desktop computer chassis. You can find some other object in your environment to clap your free hand against to generate the sound waves. And that's basically what antennas are doing, or what these electromagnetic frequencies are doing in the real world. So sometimes you have a designed antenna, like the one on the left here, where you have a rod antenna compared to the counterpoise of its reference plane. But sometimes you can do things kind of a little ad hoc. You can get creative if you have to. If you extend the center conductor of a coax out, it will pick up or radiate electromagnetic fields compared to its outer conductor. So compared to the shield that's cut back farther. I've actually had to do this when I was troubleshooting a couple times, was just take a coax and some wire and put together a monopole with about the resonant length that I wanted. Was it a great antenna? No. Did it do the job? Yeah. So these 2 conductors don't have to be part of a system. They can be just about anything. And that brings us back to our poor power supply, where we kind of started the story, right? So what happens a lot of times with devices like this is that the long cable is acting as the arm of a monopole, and then there is something in the power brick itself. Sometimes if it has a metal chassis, it could be the metal chassis. A lot of times it's an ungrounded heat sink is acting as the other conductor. And so that long cable is what really makes the electric field something you have to worry about. And the reason for that, if you look at this equation on the bottom, is that electric field goes up proportional to length. So as in a dipole style antenna, when your radiating arm gets longer, the electric field from it gets stronger. Now, by the way, I took this equation from Henry Ott's textbook. I caution people against using it as is. There are a ton of simplifications and assumptions that went into this particular equation, so don't just go around with that 12.6 times 10 to the minus 7th and assume that you're going to get the right answer. But it's very useful in terms of seeing the trends. So electric field will go up if the frequency goes up, if the length goes up, and of course, if the current flowing in the wire goes up. And then the electric field will diminish the farther away you are. So that's the over R term at the bottom. But do keep an eye on that 10 to the minus 7th term, because that's going to come back into the picture a little later. So how do you stop an antenna from radiating then? The easiest way to do that is by bringing the two elements to the same electrical potential, whatever potential that is, and you can do that by shorting them together. In our hand clapping analogy, we duct taped our hands together, and when they can't separate, they can't clap back together to make waves. So now the two arms of the dipole system are held at the same potential, and there can't be displacement current in that situation, or at least ideally there can't. And so that's going to keep the system from generating electromagnetic waves. And so this is one of the reasons that if you've ever been part of an EMC problem or an EMC troubleshooting effort, and you've called in an EMC expert, one of the first things that they do is start asking about grounding and bonding. And it's for exactly this particular reason. And we should note that not all bonds are created equal. Not all conductive connections between two pieces of metal are going to have the same effect. So I had the privilege, honestly, of switching in my career from aerospace to automotive. And now in my consulting role, I get to work with everybody, which has just been fantastic. But in aerospace, and especially I started my career at NASA Johnson Space Center, what the connector that you have on the left is called the Mill Standard 38999 connector, and it is 360 degrees of metal to metal contact. It's basically the gold standard for how to, make connections when you've got, metal over braid shields and you're connecting into something that is inside a metal chassis. You basically can't do better than this. The problem is that its price tag is also gold plated. So when I got to the automotive industry, where they're a little more cost sensitive, I actually spent time uttering words that I never thought I'd say that would come out of my mouth, which was, I think I would sell my soul for a Mill Standard 38999 connector right now. Because now, to be fair, in the automotive industry, most of the time you don't need shielding at all for a traditional 12-volt low, internal combustion engine system. Because if you've designed everything right, even when you're using chassis for current return, you just don't need the shielding. When you do need shielding, it's usually like a foil wrap kind of thing. And then most of the electronics modules in a car are housed in plastic, not in metal. So you can't terminate a shield to the chassis of the module because there's no metal to terminate it on. So instead they'll take this little wire, they call it a drain wire, and find a ground lug to the chassis of the car somewhere nearby. We try and keep that less than 5 centimeters, but that's more of a goal that's aspirational as opposed to a hard and fast thing. And, when you've got that long, thin piece of wire, sometimes it's effective in terminating your shield and keeping that shield at the same potential as the reference plane of the car, which is the chassis. But sometimes it's not. And this is such a good example of how just making a conductive connection between two things doesn't guarantee that they will stop acting like an antenna. Because, one of the other very classic forms of antennas is a loop antenna. And, obviously this is a big one. It's being used for, it was designed for ham radio. But, if you look, there is one continuous loop, from one end all the way to the other. And then they, those ends come back to, the radio or whatever receiver unit you're using, or transmit unit, transceiver. So you could say that the two ends are shorted together. They have a continuous conductive path. But in a loop antenna, of course, you're able to pick up on the electromagnetic fields flowing through it, thanks to sort of Faraday's law and that kind of thing. So it still generates a potential difference from one end to the other, and basically, most of these end up feeding into a coax, and so you're creating a potential difference between the center conductor of the coax and the outer conductor of the coax. Now, these are governed by a little bit different physics and equations than dipole setup, because again, you're reacting to the flux of the electromagnetic fields coming through that loop area. But Henry Ott had another very handy equation talking about what kind of electromagnetic fields can you expect from a loop antenna. And one of the things is that this time it's going to go up linearly compared to area. And that does not have to be a perfectly circular loop. That area can be any area enclosed by the wire or whatever geometry that you're describing. Now, much like the other equation, the electric field will also go up compared to the current, which makes sense. If you pump more current into something, if it's generating noise, it'll just generate more noise. And of course, 1 over R you'll measure less electric field the farther away you are. But here's where having these two equations side by side really highlights a couple things, because in terms of the E field itself, so just the electric field, the loop antenna has this 10 to the minus 16th term right here, compared to a minus 10 to the 7th term in the dipole. And so you'd expect much less electric field effects from the loop than from the dipole. But look at that frequency squared term. Oh boy. Some of us like to say that frequency squared term is going to keep EMC engineers in business for the rest of our lives. Because once you square something in the megahertz, so times 10 to the 6th, or getting into the gigahertz times 10 to the 9th, it does not take long before that squared term completely overwhelms the 10 to the minus 16th, and you start getting substantial E fields from even what we would normally consider a very small source. So as the world of digital electronics has evolved and has continued to evolve, as fast as as fast as it has in the last whole bunch of years, I haven't noticed switching speeds getting slower. I haven't noticed clock speeds getting slower. I haven't noticed gigabit Ethernet getting any slower. So as we keep pushing, things into higher and higher frequencies, we're going to get the loop effect even more than we had in the past. In the past, when everything was a little slower, it was really the dipole effect that you had to worry about the most, and it was those long cables that were often the thing that was going to kill you. But when we're looking at these very high speeds, we have to think a lot more closely about where there might be loops that could be radiating. Now, the solution for just like bonding two things together keeps them from being a dipole antenna, collapsing loops keeps them from being loop antennas. So the more you can route signal and ground traces together, the more you can, make sure that when you have signals returning through a ground plane, that they can get back to their source as quickly as possible, or in as short a path as possible. That's where you're going to be able to really improve your performance in terms of not having stray electromagnetic fields coming off of your board. And here's an example of this. I've got some information here from a colleague of mine, Bruce Archambault, who used to work at IBM, and some other information that's from Scott Piper, who used to work at GM. So, that's just a sort of nice illustration of the fact that industry to industry, the same problems pop up over and over again. So whether it's consumer electronics, whether it's automotive, my experience with aerospace and defense, it's all the same physics, it's all the same things, that they just manifest differently because of the unique traits of each industry. So here, if you're looking at very classic PCB trace, it's going from a source to a load, and then we're assuming that the return currents are going to flow on the ground plane beneath it. And we're really used to thinking that currents will take the path of least resistance to get back to their source. And at low frequencies, and you can see on the left, we're looking at a 1 kilohertz signal being applied at the source. At low frequencies, that's pretty much true. It takes the shortest path, which is the path of least resistance. And this is these two simulations are showing the current distribution on the ground plane. However, it does not take long. Here it's up to 1 megahertz, probably even lower frequencies would have the same effect. All of a sudden, the return currents are taking the long way around. They're sticking directly under the trace where the source current is flowing. That's the path of least impedance. So because of the way the fields line up and the energy can be translated through the dielectric of the PCB, that's actually the path that high frequency currents would rather take. The problem that we have, or one of the most common problems that we have, is when we interfere with that that longer return path by having some kind of slot in the ground plane. So I'm sure you guys have all seen, you'll have ground islands, or you'll have other discontinuities in your ground plane, for perfectly legitimate reasons. But unless you are thinking about how higher frequency currents are getting back to their source, those kind of slots can start to represent a radiated emissions threat. Now, again, there's often a pretty straightforward fix for this. If you add stitching capacitors, that lets the high frequency noise travel very close to its preferred return path without forming the large loop if it has to take the long way around. But it still blocks DC. So if you're going for DC isolation, this still maintains that effect. But let's see. And you can really see the difference in this particular slide. So this is radiated emissions at 3 meters. So very much like what you'd expect to see in a FCC test. The red trace all the way down at the bottom there, that's if you did not have a split in the ground plane at all. The green trace is if you have a split and you didn't do anything to mitigate the risk. And I think we all know that would fail radiated emissions pretty darn fast. But then the blue is what you get when you add those stitching capacitors. So again, it doesn't make it as good as it would have been if you did not split the ground plane, but it has a massive improvement in the effect. In an automotive situation, and you also get this in aerospace quite a bit, if you are using chassis for current return in the overall architecture of the platform, routing the hot wires very close to chassis is one of the ways to minimize these loop areas. And usually you want to do that anyway, right? Just for mechanical reasons, right? It's easy to have brackets that are mounted to the chassis that keep all the wires in, well-controlled bundles, and minimizes the mechanical stress on them as the vehicle goes, bouncing down a road. So, a lot of times you'll get this effect anyway for other reasons. So, but it's interesting because you would think that in a vehicle, you would always just take a ground lug, or take a from a particular module that's gotten power from the 12-volt system. You would just route the return to the nearest possible ground lug. But that is not necessarily the case. As vehicles have gotten more complex and as their wiring has gotten more complex, sometimes you find ground wires going in very strange places. One of the things I like to point out, I started working at Ford in 2016, Ford Motor Company, and I was responsible for the EMC performance of a particular high-end luxury SUV. And when you pinged the computer network, the CAN network on the vehicle, it would report back, like somewhere between 18 and 25 modules, that were controlling all the different systems in the car. 2020 was the last year that I worked for Ford, and I was testing another high-end luxury SUV. And at that point, if you pinged the CAN network, it reported back 60 modules reporting back on that network to control all the different systems. So in a space of only 4 years, you just about doubled or more the number of modules, the complexity. And of course, that means you have to add all the wiring to go to all those modules. So, as these wiring harnesses get more complex, it would be great to think that all these little ground lugs that are circled here are associated with the pink, green, and blue module connectors that are relatively close to them. But they could be from anywhere. They could be from all the way in the lower right. They could be all the way in the upper left. I once saw a particular module where it was packaged on the left side of the vehicle about midway down, so halfway down the length of the vehicle. It got, it's a nice short route from the BCM, the body control module, to this module. But then its ground wire connection went the rest of the way down the back of the car, across the back of the car, and most of the way up the right side of the car before it hit a ground lug. So all of a sudden you have this huge path, this huge loop for the current to get back to the chassis and then back to the BCM where it belongs. So it's those kind of decisions where if you're not keeping an eye out for some of the consequences or some of the implications of the wiring choices, that you can start to get into trouble. Now, when you have the opportunity, obviously you rarely have this opportunity in automotive. You almost always have it in NASA satellite missions. But if you have the opportunity to twist power and return together, that drastically cuts down on this effect. So not only have you just minimized the loops by forcing the hot and return to be very close together, adjacent loops, because they'll react to the incoming flux in opposite ways, will tend to cancel each other out. So if power and return currents are balanced, which is not always true, then twisting will cut down on emissions, and almost no matter what, it will make a cable more robust to interference. So a lot of times what you'll see is CAN, so digital communication lines, will be twisted but not shielded. And usually, again, in a well-designed system, that's all you need. The last kind of big category that I wanted to touch on in this talk is enclosures. And I'm going to be having an all-day seminar, so it'll probably be about 6 hours of content on, I believe it's July 16th through Sierra Circuit, so through the same folks who are hosting me today. And I just recently, in fact, last week, was in the lab doing some testing and measurements and found the best illustration of how enclosures can actually make things worse instead of better sometimes. I don't have the time to cram that example into this talk, but I'm really looking forward to sharing it in the longer seminar that's going to be in July, because in metal enclosures don't always act the way you think. Now, if we could put all our electronics in a solid metal box with no apertures and no seams, then especially for aerospace and automotive, I would be done. I would, get to just like retire and go home and not think about this stuff anymore. But it turns out that that you actually need interface cables for the electronics to do anything useful in the world, and that you probably need vents of some kind for like thermal control so that the electronics don't just melt. And you need some seams for lids so that, people can actually work with the electronics module. So nobody lets me put things in solid metal boxes. But if you imagine that, if you were a hobbyist working on some kind of electronics project and you were worried that, there's some kind of RF signals that might be, part of the, the signals flowing around on the board, you wanted to make sure that you didn't end up with, just radiating all over the place. So you go to Amazon, you go to Mouser, and you get one of these nice little, hobbyist boxes. It's definitely made of metal. So you put your, your little electronics project in there and you figure, okay, I'm good. But it's a little hard to tell in this picture, but this is, while it is metal, it is also painted gray. So there is paint between the lid and these mounting tabs, which means that you've got two conductors, the lid and the rest of the body of the enclosure, with an insulator, which is the paint, in between them. And what do we call two conductors with an insulator between them? We call that a capacitor. And if there are RF currents flowing on the enclosure for whatever reason that they've been induced by the electronics on the interior, if you are unlucky enough, the lid can start radiating compared to the body of the enclosure. So again, if you find yourself in this situation, there's an easy fix. You just sand the paint off the interior edge of the lid and the mounting tabs. And then you've got firm metal to metal contact when you, screw everything together. And that will probably solve that particular problem. Now, it's not going to be perfect metal to metal contact. You can see this only has bolts in the four corners. So you could imagine that there could be some bowing where it's not perfectly flat. It doesn't make a perfect fit all the way down, the edges. But, generally speaking, it's going to be good enough. But then we're also looking at slots. Now, slots can be problematic for a couple reasons. For one, they're just apertures that can allow electromagnetic fields to travel through them, right? That's one way that they can be problems, but they can act like antennas themselves. And by the way, that's exactly what I saw in the measurements that I did last week that I just can't wait to show people because it's such a good demonstration of exactly this effect. But that brings us to our last big category of antenna, which is the slot antenna. So the slot antennas take advantage of Babinet's principle, where an aperture in a solid conductor will have the same impedance and produce similar fields with reversed polarity compared to a dipole of the same made out of solid material with the same geometry. And we use these all the time, right? There are a lot of slot antennas in cell phones. It's a very convenient antenna geometry for, small flat pieces of electronics. And you can see it here. This is a marine communication system. So this is meant to, be installed on a ship for ship-to-shore communications. Instead of having an array of small little dipole elements, a boat on the ocean is going to experience a fairly severe mechanical environment. There's lots of twisting, there's lots of swaying. You've also got corrosion effects from, salt fog and everything like that. So a more robust way of achieving the same effect is to cut multiple slots in this otherwise, piece of tubular steel or aluminum or what have you. So it gives you the same, basically the same electromagnetic performance, the same antenna pattern, although again with the E and H field reversed, but with much more mechanical robustness. So we do see slots used intentionally all the time. The problem is that when you have these slots in a place where they can be stimulated by RF currents or RF potential differences, but no one's been thinking about them that way, then these same slots, cut in a plane of metal, can also look like an antenna array. Now, again, this actually has a pretty easy fix. Instead of using long, thin slots in a line, use small holes in an array. And so what the small holes do for you, it's not that they're completely eliminating electromagnetic radiation from the unit, but they are probably pushing the frequency range of the electromagnetic energy that could want to radiate from such a arrangement into high enough frequencies that you don't care. So, where long, thin apertures might end up radiating, in like the single digit gigahertz, so 1 gigahertz, 2 gigahertz, right on top of GPS or right on top of S-band. A bunch of very small holes could push any potential radiation up into the tens of gigahertz, where there are a lot fewer victims, and it's easier to keep everything protected. You'll also see this in honeycomb arrangements. So that's the element, the picture there on the lower right. Honeycomb is partly taking advantage of that effect of just having lots of small holes. But there's also a depth to the separation between each cell of the honeycomb that has an additional effect called waveguide beyond cutoff. So it actually offers almost a filtering effect. There's some really complicated and fascinating mathematics behind that. I don't have the ability to get into it here. But again, when you're concerned about both EMI at particular frequencies and thermal management, honeycomb is often the way you're going to want to go. So that pretty much brings us to kind of a whirlwind tour of things that can act as antennas, even though no one designed them to act like antennas. We keep coming back to any two pieces of metal with an RF potential difference between them can become a radiating antenna. So that can be a heat sink versus a cable. That can be a lid of an enclosure versus the rest of the body of an enclosure, or the chassis of an enclosure compared to, like the ground planes of the PCB. So there are lots of different ways that this can happen. You basically are getting capacitive coupling between things that do not show up on the circuit schematic, right? This is never happening because of an intentional component placement. But then you also have to worry about AC currents flowing in large loops. Those can also become radiating antennas, and this particular concern gets worse when in the presence of much higher frequency signals. Bonding pieces of metal together can prevent them from becoming antenna systems. Collapsing loops that currents have to take can minimize their radiated emissions. Basically, there are antennas hidden everywhere, but you can find them if you know what to look for. And if you know what to look for, hopefully you can spot them in the design phase, and you can put in some provisions for maybe you need stitching capacitors, or maybe you need extra ground vias, or maybe you need to take a second look at how boards are bonded to chassis, or chassis are bonded to cable shielding. Once you can look at, basically cast that kind of critical eye on a design, you're that much less likely to get blindsided by EMC problems when you're at the very end of your product development cycle and doing regulatory compliance testing. That's really the goal of all of us EMC engineers, is to help you guys know what to look for, fix problems in the design phase when it is cheap and easy to fix, so that you don't have to call us in during the troubleshooting phase when everybody is freaking out. I'm sure you've seen that kind of behavior. So yeah, with that, I'd like to wrap it up and open up the floor to questions. And once again, thanks Sierra Circuits for inviting me to talk, and thanks to everybody who hung out and listened for 45 minutes.
Thank you so much, Karen. You can see the question in the Q&A.
Okay, let me open that up here. It might be, oh, okay, I think it is showing in. So the first question was, isn't immunity typically the term used in EMC instead of resilience? Resilience is a separate topic. So it's a separate topic of research. So immunity is, you're absolutely right. There's immunity and susceptibility. Those are used as synonyms. Resilience is a different way of approaching design for EMC. Another one, let's see. Mentioned that 10 meters is far field, but is it really far field at 30 megahertz? So we all pretend that that we are measuring stuff in the far field, even at frequencies when we are clearly not measuring stuff in the far field. This is particularly bad in mil standard testing, because the mil standard testing that we use for aerospace and defense, and also automotive, measures at 1 meter and it goes down to 30 megahertz. So you can't even pretend you're in the far field at that point. There are a couple reasons why this is still legitimate. Part of the reason is that it's worked for 70 years. Generally speaking, if you pass these tests, even if they are a little squidgy, you will still be successful when you integrate everything. The other thing is that when you're packing everything into a car or an aircraft or a satellite, they really are packed that close together. And so you need to take the measurements at that relatively close distance to get a better sense of what the effect will be on its neighboring electronics. So again, that is, we pretend we're in the far field even when we're not. Let's see. So for the same driving current and mechanical size, which antenna would radiate better from 30 megahertz to 1 gigahertz? It's almost certainly going to be your dipole, generally speaking. Again, in that, especially like up to 500-ish megahertz, if you're seeing radiated emissions, you're probably going to be looking at cabling first. And then when you get above 500 megahertz, and you'll see people throw a lot of different numbers into that dividing line. It could be 200 megahertz, it could be 600 megahertz. Somewhere in there, the dominant effect stops being cabling and starts being loops from things like PCBs. So that's generally what we're thinking of there. Let's see. When you say we can model EMI with a loop antenna, would you say that's more like a microstrip XY plane loop or more like a vertical loop antenna? So more like a microstrip XY plane loop antenna. Yep. That's definitely, when we're thinking about loop antennas, or basically structures that end up acting like loop antennas on a PCB, then yeah, it's definitely looking more like those kind of microstrip arrangements. Okay, in the graph showing radiated emissions of the slot, shouldn't there be a resonant frequency? So there probably is, but it's probably at a different frequency range than what was on the plot. So the plot was basically 30 megahertz to 1 gigahertz, so that typical FCC range. You're absolutely right that there should be a resonant frequency that you did not see in that plot, but it's probably up in the higher gigahertz than what was plotted. Is chassis the only oh, that one disappeared before I could read it.
Oops, sorry. Hold on.
Oh, no problem. I will go to the next one. Let's see. For a twisted pair, does it increase the capacitance between them so you get more crosstalk? No, actually, very rare. I would be very surprised, because the things you're twisting together are the hot and return of of a particular either signal circuit or of a power circuit. So basically, because the signals are already related to each other, as opposed to routing CAN next to power, where you've got two unrelated systems that might experience crosstalk. That's it's, yeah, the twisting is between things that are already related to each other, if that makes sense. For a well-designed system, twisted pairs are all you need. Are there any advantages to shielding a twisted pair? Oh, yes, absolutely. So there are times when you need to shield a twisted pair. Now, sometimes that is a very aerospace belt and suspenders approach. I don't want to say cost is no object for a NASA project or for a mill standard project, but it's certainly less of a consideration than it is for automotive or consumer electronics. But there can be times, because even a twisted pair can look like essentially one conductor picking up noise from the electromagnetic environment or picking up common mode noise. We haven't talked about common mode noise, how do you say, explicitly in the talk today. I definitely will get into it in the seminar that I do in July. But twisting doesn't help with a common mode noise problem. So that's where added shielding might be the thing that you need. Let's see, lower left on page 47, does the distance between the holes affect the total radiated power? Yes, yes, I believe so. In fact, I believe, I'm picturing in my mind that I have a permanent bookmark in my Henry Ott textbook on exactly how the number and arrangement of holes and the size of the holes compared to wavelength will affect the radiated emissions from those patterns. So yes, definitely. And there's some good analytical equations that'll get you in the ballpark for finding out those effects. Hang on.
Hey.
Just
Okay.
Let's see. How is shielding or mitigating noise from E fields different from H fields? Very different. If you are mostly concerned with H fields, magnetic fields, then you are going to use ferrous material. Ferrous material doesn't do much for E fields, but it concentrates magnetic fields and directs them away from the thing that you want to shield. So ideally, you know, any conductive material, and the more conductive, the better. It shields from EF field or electric fields, and it's basically acting like a mirror. It's causing things to reflect away from the thing you're trying to protect. H field shielding, magnetic shielding, it doesn't reflect the field, it concentrates them and redirects them. So the effect is the same, you've protected the thing you want to protect, but the physics behind it is actually quite different. And mu metal, so that's mu like the Greek symbol for you know, for micro, or you know, mu. Mu metal shielding is specifically designed for those kind of applications, if that's something that you need. Hang on, take a drink. Okay. Oh, here we go. This is one that almost disappeared on me. Is chassis the only current return path in automotive circuits, or are there D ground, A ground? So inside the electronics modules, the PCBs are using the same kind of grounding arrangement as anybody else. So they've got, you know, D ground, A ground. They're actually less likely to use a specific chassis ground because they're not housed in metal. So they're much more likely to not have a chassis ground specifically from the PCB, and instead send a wire back out of the electronics module and make the chassis, the overall vehicle chassis connection that way. And so then the thing that I'm trying to do to avoid radiation is keep those ground wires that exit the module as short as possible, basically. Let's see, does it make a difference on which side? Okay, in my world, which is largely aerospace and automotive, I basically always want to ground a shield, well, and we ground, right? That still has a lot of baggage. So terminate a shield on both ends. Because you've got, you know, a solid metal chassis that everything is connected to, the chances of winding up in a situation where you only want to shield a cable on one end are very slim. However, there are two places where I know that single-ended shields are appropriate. One is for audio frequencies. So if you're trying to maintain audio quality, so you're talking, 100 hertz or maybe up to 2 kilohertz, then sometimes single-ended shielding is appropriate. My life is pretty much all 9 kilohertz and up, so I don't have to worry about that very often. The other thing is that when you are building for a fixed facility, so when you are doing the wiring for like a huge number of server racks that are going to go in a server farm in a building and never move, there might be reasons at that point to single-end a shield. But generally, just terminate at both ends, just like always. Basically, it's the exceptions are very rare. Let's see. Can you use a slot antenna on a wrapped surface? I'm assuming that's probably warped surface rather than flat surface. Yes, absolutely. And there's some people doing fascinating modeling and research on that topic. There are all kinds of things people are doing on, I think they call them conformal surfaces. I have in the past managed an RF group at EMA, and they've been doing some R&D work on those kind of topics, and it's absolutely fascinating. Let's see, isn't it more rational to speak about the magnetic field radiated from a loop instead of E field? I mean, yes, it is. The reason that we're comparing E fields in a slide like that is because the regulatory limits up until recently have almost always been expressed in terms of the E field. So you're almost always taking your regulatory measurements in units of dB microvolts per meter. Now that has changed, especially in the electric vehicle space, because CISPR 36 basically lowered the radiated emissions frequency range down to 150 kilohertz to 30 megahertz. And there they are using loop antennas, and the units of measurement are dB microamps per meter. So they are specifically measuring the magnetic fields. So you're absolutely right. There's the reason for talking more about E fields, even when we're talking about loop antennas, is because of the way the regulations are worded. Okay, let's see. Coming up to the end here. Seen some papers describing testing using near H field probes to test for far field emissions. Oh man, SEC limits in the near field. Man, it would be great if you could get really tight correlation between near field measurements and far field performance. The problem is, and you can see this in some very fancy antenna modeling, the fields in the near field are so jumbled because they haven't settled down into plane waves yet, that the correlation from near field to far field is pretty poor. Now, going the other way, if I have a unit that has failed EMC limits, and then I bring it back to a non-certified lab to do troubleshooting, if I can establish using near field probes that I have high emissions at the same frequency that was failing the official test, then I could definitely kind of key onto that as part of my troubleshooting mitigation, right? So if I can identify using near field probes the same frequency and standing out, then I've got pretty good confidence. And if I can make that better on the near field probe, it will probably also get better in the regulatory testing. But yeah, I've actually also been doing some research on my side, specifically about near field to far field, and had some people looking at this kind of correlation, and the math gets just insanely complicated. So I'd be very shocked if a regulator wanted to wade into those waters. See, biggest noise sources in a car. So in a traditional internal combustion engine, the biggest source of noise is also one of the easiest to control. Well, now we have fuel injection. So the spark plugs used to be the biggest source of noise in a car. And it used to be all you had to do for EMC in the automotive industry was make sure that the engine block was grounded so that the spark plug noise didn't affect the AM radio. And basically everything else took care of itself. Oh my goodness, how times have changed. So let's see, pumps and motors are the biggest source of noise usually. That's what I ended up chasing the most. Again, I was often worried about protecting AM and FM radio. So the kind of frequencies of noise that fuel pumps would put out were definitely in frequency ranges that could affect AM and FM radio. In electric vehicles, it's almost always going to be your inverter that takes DC power from the battery, transforms it to AC power to actually drive the motor, or it's going to be your DC-DC converter. So when you've replaced, basically DC-DC converter takes the place of the alternator, it's converting high voltage power from the battery pack to 12 volts. Those are the two things in an electric vehicle that are the largest noise or most common very bad noise sources. And we'll probably call this the last question. Thank you guys for so many really excellent questions. I really appreciate it. Returning to cable shielding, recommendations to usually ground at one end only. If you ground at both ends, doesn't that create a potential loop antenna? Okay, so I get this a lot. Imagine that you have grounded, so you've got a metal box, a cable running to another metal box, and they're both sitting on top of a chassis. Actually, that's the exact situation here, I think. I've got a better one. Yeah, loop area. So if there's shielding here, the question is, if it's connected here and connected here, then you have this particular loop. The currents flowing in that loop are always going to be stray currents, right? Because you've shielded off everything that's actually intentional. And the other thing is that the shield itself and the metal enclosure and the metal chassis is keeping any of that noise away from your sensitive electronics. So yes, you do have the potential for currents to be flowing in that loop, but they are flowing on the outside of the shielding, which is where you want them, if that makes sense. Whereas if you have a version here where you've got, imagine this is just a shield and the rest of the conductors go all the way. This looks exactly like a monopole antenna. So now you can really pick up noise on the shield that is, radiating with a potential difference compared to chassis or compared to the enclosure. And the problem is when the shield is single-ended, there's a really good illustration of this, a diagram of this in Henry Ott's textbook. The shield can then re-radiate the noise into the conductors that it is supposed to be protecting. So it's the fact that a single-ended shield can transmit energy into the cable harness with a much higher transfer impedance or a worse transfer impedance than if it were double end terminated is the reason why we recommend almost always double ending the shield or double end terminating the shields. So I hope that overall gave you more clarity than confusion. And once again, I'd just like to thank Sierra Circuits and thank everyone for who stayed online.
Thank you so much, Karen. Thank you everyone for joining. I will send you the recording and slides at the end of the day or tomorrow morning, promise. Thank you everyone. Have a good day. Thank you so much, Karen.
Great, thank you.